You are evolving into a mantis shrimp. Well, not literally. You are not about to grow flippers, move into the ocean, and start punching snails at the speed of underwater gunfire. But the idea behind the title, "Why is everything evolving into mantis shrimp?" isn't just clickbait. It's our fun way of talking about one of evolution's favorite party tricks, pushing totally unrelated creatures towards surprisingly similar solutions. When the environment demands peak performance, and in the chaotic world of light underwater, the mantis shrimp's visual blueprint is one of those solutions. Because here's the thing, when you live in a place where light bends, scatters, shatters, and behaves like it's glitching on purpose, having normal eyes is basically running life on hard mode. So, evolution goes, alright, new plan, and cranks the sensory hardware up to ridiculous levels. Some animals sharpen contrast, some specialize in low light. And then, in the far corner of the genetic workshop, the mantis shrimp shows up with a build so overpowered it feels like a cheat code compound. Eyes with at least 16 kinds of color receptors, ultraviolet channels, and the ability to read multiple forms of polarized light, including circular polarization, which literally no other known creature can consistently detect. This isn't just eyesight, this is evolution's premium optical upgrade pack. So when we joke that everything is evolving into a mantis shrimp, what we really mean is that evolution loves reusing whatever works, and the mantis shrimp-style problem-solving approach to vision is such an efficient body plan hack that physics basically keeps nudging animals towards some version of it. But why does this particular design work so well? What makes it such an effective blueprint, one that evolution keeps stumbling into whenever light gets tricky? And what is the strangest visual trick the mantis shrimp uses to pull it all off? Those questions lead us straight into the main story, beginning with a very humbling truth about our own eyes. You are basically colorblind. Not metaphorically, not in a poetic we are all blind in some way kind of way. I mean, biologically, compared to a mantis shrimp, your eyes are basically running on discount hardware from the clearance shelf. And here's the absurd part. This is not an exaggeration. This is not a meme. This is what the scientific literature, actual journal articles with reviewers who haven't smiled since 1998 tells us. Because the mantis shrimp, a tiny neon-colored sea gremlin with anger issues, is equipped with one of the most over-engineered visual systems in the entire animal kingdom. 16 color receptors, ultraviolet sensitivity, the ability to read polarized and even circularly polarized light, built-in optical filters, eyeballs that can roll and calibrate themselves like a camera in manual mode. Meanwhile, you and I are out here struggling to find our phone in a dimly lit room. So today, we're diving deep into the eyeball madness of the mantis shrimp, the creature whose view of the world makes ours look like someone forgot to turn the brightness up. And yes, by the end of this video, you will probably question whether you deserve your current pair of eyes at all. Let's begin. Let's start with the basics. Humans have 3 types of cone cells: red, green, and blue. Birds have 4. They get an extra ultraviolet channel that makes their world look like a rave party. Butterflies, they sometimes have 5 or 6. Impressive. But then the mantis shrimp walks into the evolutionary chat with a minimum of 16 separate receptor types, each tuned to its own specific slice of the electromagnetic spectrum, like an absurdly over-organized librarian who thinks Dewey Decimal isn't enough. These receptors cover everything we see, everything birds see, everything butterflies see, and then a whole bunch of wavelengths nobody without a crustacean brain has any business perceiving. When scientists discovered this, the scientific community collectively said, "Excuse me, what?" Then they checked again and confirmed, yes, this little ocean punch goblin sees the world through 16 rainbow channels. But here's the plot twist. More receptors does not automatically mean better color vision. In fact, humans, yes, our pitiful 3-cone selves are actually better at differentiating subtle color differences than mantis shrimp are. Wait, what? How does that make any sense? Here's how humans mix color signals in the brain. We take 3 inputs and blend them into millions of shades. Mantis shrimp, on the other hand, don't blend. They tag wavelengths directly. Their eyes work less like a painter mixing pigments and more like a barcode scanner that instantly categorizes whatever it sees. This might feel like a downgrade, but for them, it's peak efficiency. Because while humans are doing brain math every time we see a color mantis shrimp, outsource the job entirely to the eyeball hardware itself. It's like they have 16 preset color channels that tell them, this is 434 nanometers. Don't think, just act. Evolution wasn't trying to give them pretty rainbows, it was giving them speed. Now let's get into the truly unhinged part, polarization. Humans cannot see polarized light. The closest you get is when you put on sunglasses and go, wow, the glare is gone. Magic. No, not magic. Just physics doing physics things. We see the effects of polarization, but not polarization itself. The mantis shrimp, they see it. Directly, unavoidably, constantly. They see linear polarization, light waves vibrating in one direction. They see diagonal polarization vibrating at angles. And incredibly, they see circular polarization, which means light twisting as it moves clockwise or counterclockwise like microscopic corkscrews. At this point, calling them shrimp feels rude. This is not shrimp behavior. This is spy gadget behavior. And they are, as far as we know, the only animals on the planet that detect circular polarization intentionally and consistently. Humans invented liquid crystal displays and thought we were clever. The mantis shrimp has been doing the same thing for millions of years with its eyeballs. Why would evolution give this level of optical insanity to an animal that spends most of the day punching things? 3 major reasons. First, hunting. Mantis shrimp strike with one of the fastest movements in the animal kingdom. Their club-like arms accelerate so quickly that they literally cause water to boil through cavitation. To hit prey hiding in sand or nearly transparent or blending into coral, they need a visual system that can cut through camouflage and distortion. Polarization is perfect for this because reflections off biological tissues often reveal patterns invisible in normal light. A fish might look like a boring blur to us, but under polarization, its scales might outline itself in high contrast. Second, communication. Many mantis shrimp species have reflective patches that bounce circularly polarized light. Only others of their kind can see it. Imagine having a secret glow-in-the-dark badge that only your friends can detect. That's what they do signal to mates, warn rivals, or claim territory using visual information that predators can't decode. That's not just useful, that's elite-level evolutionary gatekeeping. The third reason is navigation. Underwater light scatters, bends, and behaves like it's trying to prank every animal that relies on vision. Polarized light, however, changes in predictable ways as it moves through water. By reading polarization patterns, mantis shrimp can extract cues about the sun's position, the environment's structure, and even the time of day. They basically have a natural compass built into their retinas. Meanwhile, some of us can't tell east from west without checking our phones. If this video made you realize your eyes are basically the free trial version of vision, hit like, share, and subscribe. We've got plenty more strange creatures waiting for you. Now let's talk about eye anatomy, the part where things escalate from that's cool to, okay, we need to talk. Mantis shrimp don't have simple spherical eyes like humans. Their eyes are mounted on flexible stalks, each capable of moving independently, like twin periscopes doing improv. Imagine if your left eye wanted to look at the fridge and your right eye wanted to watch Netflix. That's the level of independence we're dealing with. But the real magic is in the structure. Each eye is divided into regions, including a specialized middle band packed with the receptors for color and polarization detection. This middle band functions like a biological scanning unit, sweeping across the landscape and analyzing visual data with ridiculous precision. And get this, mantis shrimp roll their eyes, not metaphorically but physically rotating them to adjust polarization sensitivity. They spin their eyeballs like camera lenses, dynamically tuning their perception based on the environment. No other animal does this. None. When scientists first observed eye rolling in mantis shrimp, they described it as unexpected. That is scientist language for, we have no idea what is happening, but it is terrifying and amazing. So, let's zoom out. Why do mantis shrimp have such ridiculous visual systems when most animals get by just fine with simpler designs? Well, evolution doesn't create things because they're cool. It creates things because they work. And the ocean, particularly shallow tropical waters where mantis shrimp live, is a chaotic light environment, full of reflections, distortions, scattering, and shifting spectrums. If you build your survival strategy around raw speed and surprise attacks, you need a sensory system capable of slicing through that chaos. Evolution solved that problem by turning the mantis shrimp into a living optical machine. Most animals reuse generic visual designs because they're cheap and functional. The mantis shrimp is an anomaly, a creature pushed so hard by environmental pressures that it ended up with an entirely different blueprint, one that looks like it was drafted by an engineer who drank too much coffee and said, "What if we just add more?" But here's the deeper question. What does their world look like? The honest answer is, we don't know. We can describe the physics, we can describe the anatomy, but color and perception are subjective experiences tied to neural wiring. Humans cannot imagine colors outside our spectrum, because imagining requires neural pathways we do not have. Telling a human to imagine ultraviolet is like telling a fish to imagine Wi-Fi. The mantis shrimp sees a world full of signals and contrasts we can't mentally simulate. You could try to approximate it by boosting saturation, shifting hues, and overlaying polarization maps, but that's like describing Beethoven to someone who's never heard sound. Our brains simply weren't built for it. Now let's add one more twist. Mantis shrimp eyes aren't just good. They might also be energy efficient. Human color vision relies heavily on brain processing. We interpret color using large-scale neural computations. Mantis shrimp offload this work to the eye itself, meaning their brain doesn't have to waste time analyzing hue differences. Their receptors and microstructures do the heavy lifting. This is not a superhero upgrade, it's a performance optimization. Evolution didn't give them more power, it gave them smarter hardware. Like a gaming PC with a GPU that does all the rendering so the CPU can chill. And speaking of hardware, the mantis shrimp's eye design has inspired actual technological innovation. Engineers studying their circular polarization detection have experimented with new camera sensors and medical imaging systems based on the same principles. Some cancer cells reflect circular polarization differently than healthy tissue, meaning mantis-shrimp-style sensors could one day help doctors spot tumors. So yes, the angry rainbow bug may help diagnose cancer. Life is weird, but the story doesn't end with color and polarization. Mantis shrimp eyes also have depth perception using only one eye. Humans need both eyes for stereoscopic depth. Mantis shrimp, each single eye can calculate depth independently using trinocular vision, 3 overlapping visual fields per eye. Imagine a camera that has built-in distance measurement without needing a second camera. Now imagine having 2 of those cameras, each rotating, calibrating, tuning, and analyzing light in 16 channels. This level of visual redundancy is absurd. But for an animal that charges headfirst at prey with the force of a bullet, it's probably a good idea to double-check what you're punching. Let's step back once more and talk big-picture biology. A lot of people think evolution is this magical force that creates fantastic creatures on purpose. But evolution is not a designer with a plan. It's a collection of small tweaks that happen to work. Physics and environment do most of the limiting. That's why so many animals have similar shapes and similar sensory systems. They're the solutions that physics approves. But every now and then, a lineage slips through a loophole. The mantis shrimp is one such loophole. It is not random weirdness. It is a creature forged by the specific demands of light, water motion, and raw mechanical violence. Their bizarre eyes exist because in their ecological niche, nothing else would work as well. Evolution isn't infinite imagination, it's trial and error with consequences. And in the mantis shrimp's case, trial and error resulted in a biological masterpiece of optical engineering. So here's your friendly reminder, the next time you look at the ocean and think, peaceful blue water. Just remember that beneath the waves is a small creature currently perceiving ultraviolet signals, reading polarization, calculating depth, trilaterally adjusting visual filters on the fly, and possibly communicating using secret spiraling light messages, all while preparing to punch a snail hard enough to cause a tiny underwater explosion. You are not in danger, probably, but you are absolutely being outclassed. Thanks for watching. If you enjoyed learning why your eyes are basically the free trial version of vision, check out our video on animals that evolved impossible physics hacks. And hey, leave a like, subscribe if you want, and I'll see you in the next one. Stay colorful, or at least upgrade your settings a little.